Hey, so in this video I'm going to do my best to show you a proof that the limit as x approaches 0 of sine x over x is 1. And we're going to be using something called the Squeeze Theorem. So if you have background of the Squeeze Theorem, that would be best. So the Squeeze Theorem is basically just saying that what we're going to try to do is ensure that this function is between two other functions, and then show that their limits equal the same thing. So let me just walk you through a few of the basic things that you'll need to know before we start. So the Squeeze Theorem. And it basically just says if f of x is less than or equal to g of x, less than or equal to h of x, around a certain value, let's just say near x equals c, and the limit as x approaches c of f of x equals the limit as x approaches c of h of x, and let's say that both of them equal some letter L, then that implies that the limit of the limit as x approaches c of g of x equals that same number, that same limit. Okay, so that's the theorem that we're going to use in order to prove this statement up here. Another couple of things that you'll need to know is basically the arc length formula. So let's draw a circle and just recall a couple of things about the unit circle. So first off, the unit circle has a hypotenuse, or a radius of 1, sorry, and that the arc length formula is radius times theta. Now, what is theta? Well, theta is how much this angle is open right here, okay? But they said that the radius was 1, and if the radius is 1, then our arc length is just 1 times theta. In other words, our arc length out here is the same thing as theta. All right, so that means that the length of this arc is theta units long, whether it's in inches or centimeters, some kind of linear measurement, right? Okay, another couple of things that you'll need to know, and I think maybe I should draw a larger circle for this one. So, and maybe I can just draw the right side of it, just so we can kind of get save a little bit of space here on the page. So we still have your radius of 1. Still have that radius there. Okay, so I'm going to draw a vertical line, and most people know, they've memorized the unit circle at this point in this video, right? So you guys call this sine theta because it's the y value of this right triangle. And I guess I will do some more convincing on why that is sine theta. But this is sine theta because if you have theta and it's inside here, and you wanted the opposite divided by the hypotenuse, well, the opposite side divided by the hypotenuse in this case would just be this opposite side, and the hypotenuse would be 1. So that is exactly sine theta, right? So I'm going to write this sine theta on that vertical segment right there. Okay, so in order to kind of get this idea down, basically what you're going to want to do is extend this triangle because there's another trig relationship right there that we need to cling on to, okay? So this is still an opposite side, but we don't have the hypotenuse anymore, but we do know what the adjacent side is, because this adjacent side is still length 1. So this opposite side, this time it's opposite divided by adjacent, and opposite over adjacent is just tangent theta, okay? So the length of this vertical segment is tangent theta. And the length of this curved segment, we've already set it, I just don't have it labeled on this picture. The length of this segment is actually, or curved piece is theta. Okay, so you can tell automatically, just by the way this picture is drawn, you can tell that sine theta is the shortest piece, and theta is the next piece, and then tangent theta would be the longest segment. Okay, that would have the longest length. So let's take just a minute to talk about one other detail. Typically, when you take a limit as x approaches 0, you'd have to go from the right and from the left. Now, in the unit circle, there's no real way to go from the right and from the left, but this is the only 0 on the unit circle, right? So if this is the only 0 on the unit circle, then that means that I would have to take theta as theta is getting closer and closer to 0. So basically in the first quadrant, and theta as it's getting closer and closer to 0. So that would be in the fourth quadrant. And I'm talking about quadrants so that you guys can kind of think about what your symbols would do there. So this would be your first quadrant, positives, all positives, and then your fourth quadrant, and maybe positive x values, negative y values. Okay? So anyway, let's take a look at this, because this is interesting, because I told you we're going to be using the squeeze theorem, and we have a function, we have this function theta that's between sine theta and tangent theta. So let's start with that. If sine theta is less than or equal to theta, which is less than or equal to tangent theta, then let me see, what we're going to try to do is we're trying to get sine x over x, right? And in this case, we're going to use theta. So sine theta over theta. That's our goal. Well, I don't have sine theta in the middle, but I need sine theta in the middle. So let's just take everything and divide by sine theta. Sine theta over sine theta is 1. 0 over sine theta is 0 over sine theta. Now tangent theta divided by sine theta, well, let's think about its definition. Tangent theta is sine theta over cosine theta. And I'm supposed to be dividing by sine theta. So you can see that the signs can cancel. And you'll need your placeholder on top. That'll be a 1 on top. So that's 1 over cosine theta. So as we're working through that, let's consider that we have theta over sine theta now, and our goal is sine theta over theta. So what we're going to try to do is just flip everything, or invert everything, or reciprocate everything, okay? So now let's think about numbers. If this was something like 2 is less than or equal to 3 is less than or equal to 4, and then I flipped everything, this would not be true. 1/2 is not less than 1/3. 1/2, remember, is 0.5. This is 0.67, let's call it, and this 1/4 would be 0.25. So it would not be true to write it with the same inequality symbols. So I'd actually have to flip those inequalities. And that keeps this true. Okay? So let's go do that. Let's invert 1. 1 divided by 1, or we flip 1 and it becomes 1. Change the inequality symbol. Have sine theta over theta. Flip the inequality symbol. And then 1 over cosine, well, that would just become cosine theta. Okay? So, great. We are in the position to solve and find this limit. So or to prove this thing. So, we're trying to find the limit. So basically, what I'm going to do is maybe, you know what, one last step, one thing that I would probably like to do, just because I like the arrows pointed this way, so I might just rewrite it. But all I'm going to do now is find the limit as x approaches 0, theta approaches 0 of cosine theta. So I'm taking the limit of all 3 sides of this inequality. Now I still will not be able to find this limit on the inside, but knowing the limits on the outside might help me with the limit on the inside. Okay? So I think finding the limit as theta approaches 0 of cosine, well, if I just substitute in 0 there, cosine at 0 will be 1. So 1 is less than or equal to this limit sine theta over theta. And then if I substitute 0 into this, well, it's a constant function. It's always 1. So if this limit is between the values 1 and 1, then this limit must be 1. So by the Squeeze theorem, the limit as theta approaches 0, sine theta over theta must equal 1. And that is worth smiling about. All right, so that is a property that I want you guys to know. Now, you don't need to know all of the steps of the proof. The proof is happy, it is nice, it is cool, it is clean, it is awesome. However, what you really need to know is this piece right here, and be able to apply that piece to problems that you are presented with. All right, so that's the proof. I hope that wasn't too bad. See ya.